Okay. We'll be starting in maybe 10 seconds now. I wanted to make sure, I know that, another meeting, a lot of people are coming from just ended. And David, you're able to hear me?
Yep, we're good.
Great. Okay. So I'm going to begin a little bit briefly about the logistics of today's meeting, just to make sure that we are all on the same page. And then I'll do the formal introduction of David. First off, thank you all very much for joining for today's meeting, for the talk. I'm very excited about it, and I'm glad to see so many people here. When you are not asking a question, please mute your microphone. We would like, ideally, for as many people as possible who are comfortable doing so, to have their cameras on. And this way, it will create an environment that is like a talk for David, because otherwise, it is much better to actually speak to real people. I know we are all real people, but it's hard to say that if we can't actually see camera. So ideally, if it works for your scenario, to have camera on. The other logistical thing that I wanted to mention is that we are going to use the group chat for raising hands, because otherwise it's very hard to see who is actually asking a question. So when it's time for questions and answers, when time for Q&A, please type hand. And that way we know what order to call on people. The other thing I will say is that because of the structure of the virtual interview and in general, it's going to be hard to do Q&A during the middle of the talk. If you do have a Q&A type question that's just really important for clarifying, then please do type in the chat. I'll be monitoring it, and I will kind of interrupt, I'll mention it to David that that's happening, but it's a little bit harder to interrupt someone when we're not actually in the same physical space. So ideally, we'll hold the questions till the end. And so that's it on the logistics part. Okay, so with that, it's a great pleasure for me to introduce David Kohlbrenner. She and I are hosting David. David comes to us, originally got his PhD from UC San Diego. I said originally got his PhD, but he actually still has his PhD from UC San Diego. And is now a postdoc at UC Berkeley. David's kind of work is in computer security, but with a lot of connections to a bunch of other areas, especially operating systems and architecture. And some of the adaptations of his research that have been employed in technologies that many of you might use on a daily basis, such as your web browser or the Linux kernel. Some other things that I think are kind of valuable for us to know in the computer science department is that David was also one of the founders of the Capture the Flag, or early members of the Capture the Flag team at CMU. Those of you who know Capture the Flag competitions and security competitions know both of just how broad they are in terms of the knowledge base and information needed to be successful at them, as well as how strong the CMU team was. So it's great hearing about that, and I'd love to learn more from David at some point about these Capture the Flag teams. David also has a lot of experience on teaching. In fact, he was one of the people that initiated a new computer science course at UC San Diego, designed to help bring new students knowledge about how to be an effective user of operating systems. And I'm sure I'm mischaracterizing and not presenting the full depth of that, but great sense of breadth and diversity. But again, for the purposes of today's talk, David will be talking about his research in computer security, again with connections to architecture and operating systems. And so with that, I will virtually hand it over to you, David.
Yeah. Thank you so much. That was a fantastic introduction. Obviously, I'm David Kohlbrenner. I think you should be able to pin the video and everything, and it should stay nice and good. So today I'm going to be talking to you about building trusted systems on top of leaky abstractions. And the challenge here comes from the core way that we solve problems of complexity in computer science, which is that we build layers upon layers of abstraction in our systems. And this is a really good idea. This is why you don't worry about transistor layouts when you write JavaScript applications. The problem is that the details of underlying implementations can leak and become visible to higher levels of our abstraction, and this can sometimes happen in very dangerous ways. What seems like an arcane performance optimization detail can in fact compromise a well-designed and security-focused system. And I'm specifically interested in cases where this is coming from hardware, so where hardware affects software security. what we've seen over the past few years, especially, has really reinforced the idea that the performance takes all as a design methodology for hardware is fundamentally at odds with building a secure system. So I work on how to build trusted and secure systems kind of despite this unfortunate reality we live in. And that means things like new security-aware abstraction mechanisms and cases where we kind of have to change the way that the problem is structured and go after the adversary's assumptions. So when I talk about this stuff, there's kind of two broad things I want to keep in mind. The first is that when we go to look at a problem, we need to consider our entire system stack. We can't consider software or hardware in isolation. When we do that, we're going to miss critical details. And the second is that there will kind of always be another bug. There will always be another vulnerability that we discover. And so when we build secure systems, we should build them around notions of kind of agility and reactivity, and use provable and verifiable methods where we can to close off entire classes of problem. And so when I talk about a problem in security kind of crossing stacks, I'll give you an example right now that we'll actually walk through in kind of more detail later in the talk. There's a case where kind of what seems like a minor performance detail demolishes our expected security guarantees. So in this case, we're a kind of average web browsing user. We are running a well-designed, secure, and up-to-date web browser. And on our system as well, we have certain things that we would prefer to keep private. Documents, our own web browsing history, pseudonymous usernames on social media websites. We all have kind of a pile of things that we don't expect random websites to get access to. Now, inevitably at some point, we're going to connect to an adversary's web server. We will click on a link that we should not have clicked on, and now we're talking to an adversary. And the adversary will send us a web page, and we will begin to render that web page. Now, this is the point at which our web browser is supposed to keep us safe. The adversary should not be able to install malware on our system and take it over. They should not be able to steal our private documents, our web browsing history, our private information. The attack that I'm going to go through, though, in this scenario, the attacker is going to embed invisible iframed copies of private data, and then without even looking at those copies, they are going to extract pixel by pixel the content of our secrets. Now, this is done because the adversary is going to be able to observe the rendering time of content on the web page and use that to infer our secrets. The unfortunate part here is that this rendering time is not based on decisions made in software and is in fact not visible in software. It's because of decisions made in the chip architecture. And so this is an example of where an abstraction failure occurs. There's a leak in the implementation from the bottom of our system all the way up into the high-level software security. And so when I talk about this leakage and abstraction stack, there is actually a stack I have in mind here. At the top, we have some set of security objectives. In our previous case, that was that we expect the web browser to keep private content private and not give it to random web pages. And there's some application that enforces or inherits this set of security objectives. In that case, this is a web browser. So it's actually quite a complex application with multiple layers inside of it. Below that, we have a privileged software layer, so an operating system in general. And then we have some number of layers of kind of hyper-privileged software. So this is hypervisors and firmware and system management modes. A modern Intel processor has 3 to 4 of these kind of stacked on top of each other. And then finally, we actually have the chip architecture itself. And this kind of thought process is enough for the things and projects that I'll be talking about today, but it is worth keeping in mind the fact that we do actually run these programs on real silicon that someone has made, and the physical layer can sometimes matter. And there are several high-profile examples where security was impacted by physical effects in processors and systems. And so my work is, again, on building kind of trusted systems despite these broken abstractions. And there's two pieces to my research. The first is an adversarial side. This is about developing kind of new classes of attacks that change what we thought an adversary was capable of doing. And so this is stuff like cache attacks that operate even with entire classes of defense in place, even if those defenses are perfect. The attack I showed you a second ago is actually based on details of floating point timing performance, where these tiny little performance details break our system down. And these projects can require us to look all across the stack. So the floating point one, for example, right, requires us to look at the chip architecture all the way up to the web security model. And that project in particular, for example, we found a bunch of vulnerabilities in a number of major web browsers, including Firefox, Safari, and Chrome, and worked closely with those vendors to repair them, including some really major changes to Safari. But I view this as almost a motivational side to the other half of my work, which is on building defensive systems. So we take the knowledge that we've gained from drilling through our stack, developing new types of attacks, understanding the depth of the problem, and then try and build something safer on the other side. So this is everything from how we can generate random numbers on embedded systems, to designing web browsers for defending against entire classes of attack, to kind of building more trusted and flexible systems from the architecture on up. And one thing I put a lot of emphasis on here is that deployment matters. I try and build systems that have real world impact and can get between users and attackers. So recently, the Linux kernel has been adopting a number of the techniques that we developed and evaluated for random number generation in kind of limited and tough situations. This browser defense project, post-publication, I worked very closely with Mozilla to get the prototype adapted into deployment where possible. And in fact, Chrome and Edge independently adopted some of the techniques that we proposed in this work to get a handle on some kind of very dangerous cases of leaky systems abstractions. And while the Keystone project is actually being published this year, we've actually been working on it for several years with hardware manufacturers to try and get the system that we are building out there and ready into products to make things like safer Internet of Things devices. So today I'm going to have a chance to kind of talk about 3 of these projects with some detail. The first will be, I'll kind of go through in detail what was happening in that attack example I gave you earlier and show you the kind of types of vulnerabilities that we found and why they're unusual and interesting. The type of attack we're going to demonstrate here is actually the first time that this type of attack has ever been demonstrated on commodity processors. The second project will be using that as a bit of motivation. We'll talk about how we can solve kind of the entire class of problems of timing attacks in general in web browsers by challenging the attacker's core assumptions. And then the last project I'll talk about is my most recent one, which has been going on, as I said, for about 2 years now. We're going to be trying to build trusted systems from the ground up. We're going to be tackling some very challenging attacks and threats by building a different type of more flexible security abstraction. So since both this and some other parts of this are going to talk quite a bit about timing channels, and notably I'll be talking about a new class of timing attack or timing channel called an instruction data timing side channel, I want to kind of quickly go through how timing channels are going to normally work. So in a normal timing channel scenario, it's relatively straightforward. We're going to look at a covert channel. So this is an intentional case of a timing channel. We have a sender and receiver, which are processes on the same system. They're not going to send each other explicitly data. They're going to instead leverage the fact that both of them have access to a shared storage device, and they're not going to exchange data through it. What they'll do is construct 2 scenarios. In the first scenario, the sender does nothing. And when the receiver makes a request to the storage device, they get their data back relatively quickly. And in the other case, the sender is going to make a whole bunch of requests to the disk, putting it under heavy contention. And so when the receiver makes their request, they get their data back much slower. And so we'll call this scenario the sender implicitly sending a 1, and we'll call the other scenario the sender implicitly sending a 0. And with 2 symbols, we can construct a communications channel. And now they can talk to each other. Now, I'm talking primarily today about side channels. And the difference between a side channel and a covert channel is that a side channel is an unintentional covert channel. The sender's not trying to send information. And so this is an example of what a timing side channel normally looks like. You have a branch in the code, and you have a conditional that is based on a secret. Now, these are nasty problems to solve. And what we're going to see is that solving this problem here in the source code in isolation is effectively impossible. We are hamstrung by the realities of the incredibly complex and leaky systems that we actually run. So whenever we talk about a side channel or an attack, there is always some set of security objectives that we're going after. And in this scenario, we're sticking with this kind of browser concept. So we're talking about a scenario in which the adversary is attempting to steal private information about a user. This is not a binary success failure for the attacker. This is they're trying to steal your web browsing history, information about your email subject lines, lots of different type of private data bit by bit. And we're going to use a kind of well-known attack structure here to demonstrate something new. So in this scenario, the adversary gets a victim to click on their web page so that they visit the web page. The attacker is then going to create an iframe that has special user content visible in it. So this, again, might be usernames, it might be private documents. Now, the good news is browsers are smart, and there's a policy that says that an attacking web page cannot look at the content in this iframe. This is the same origin policy. It's a core part of web security. When the attack succeeds, though, the attacker is going to be able to extract pixels from this iframe. And that's why this is a pixel stealing timing attack, where they're not going to programmatically access the iframe and kind of just print out the content. So this is going to happen because the browser exports a graphics API that an attacker can ask the browser to do computation or filtering over pixels that it does not control. So the adversary can't look at this content, but it can ask computation to be done over this content. And it can specify some parameters over these filters. So in detail, what's happening is adversary creates an iframe, this embedded content that it can't look at. It's going to select a pixel that it wants to read. It'll do this one pixel at a time. They then expand this pixel into many copies of it. We're going to then binarize it to black and white for simplicity here. Again, adversaries still can't see these pixels, but they can manipulate them. They're then going to run one of these filters over it, and the browser does the filter rendering. Again, adversary can't see the output, can't see the inputs, but they can see how long this filter takes to render based on the frame rate of the web page. And so this graphics API allows things like skewing and clipping all the way up to complex 3D lighting. Now, they don't care about the output because this is a timing channel. What they care about is how long that filter took to render. Based on how long that filter took to render, they're going to then classify that original pixel as either black or white. Now, if this is going to happen, it must be the case that these filters run in variable time based on the color of the pixel. So why would this happen? Well, the short answer, the simple answer, is a previous bug that used this type of attack model, which is we have a classical timing side channel. We have a branch in part of the rendering code. There's an if, there's an else. The if happens to, in a complex way, be based on the color of the pixel, and these two branches take a different amount of time. Now, the good news is they fixed this, right? And what they did was they brought over a style of coding that comes from the cryptographic world, which is constant time coding. And in this, you avoid branches in your code, you avoid secret-dependent cache loads, you write a bunch of kind of ugly bit operation hacky stuff that looks kind of like this. Now, this should be pretty safe. This seems like we have solved the problem. We've removed all branches from these filters, and they should be pretty safe. But the attack that we demonstrate here is going to leverage the fact that these filters are implemented using floating point math. We're going to construct an instruction data timing side channel, which is a side channel where the timing variation comes not from software path and software branches, but from the amount of time it takes an individual instruction to execute. This is actually the first demonstrated instruction data timing side channel on kind of commodity grade processors. So if we have variable time instructions, we need to know how we can use them and what they are. We don't actually have to look super far to find some. We can just look at the number of cycles it takes for a common Intel processor to execute various multiplies. So in this case, this is the number of cycles that it takes for a lot of different operations. Look at just this as an example. So -1e -320 times either 1 or 0 is going to take about 6 cycles or 130 cycles, depending on if it's 1 or 0. And so this is enough right away for us to construct a timing channel. Let's say that there's a scenario in which the secret is either 0 or 1, and it happens to be multiplied against this really tiny 1e -320 value. The adversary doesn't need to see the input, and they don't need to see the output. They just need to know how long the multiply takes to execute, and they can tell what the secret was. Now this happens because that 1e negative 320 is a special class of floating point value. It's like what's called subnormal or denormal floating point value. And they have unusual performance characteristics and a different internal representation that causes this. Now, multiply is going to show you some slowdowns here on this processor and on most Intel processors. But the more complex the operation you look at, the more unusual the behavior you see is. So if we just look at divide, we still see slowdowns due to these subnormal or denormal floating points. We also see speed ups for some classes like zeros, and unusual outliers that have their own unique, consistent timing profiles. So the more we're able to get timing information out of this system, the more bits of information we can extract about content per operation. So with these pieces in mind, let's go back and look at our filters. So can we find an interesting case of this math being used in these filters? So the example I'm going to give here is from a real bug that we found and demonstrated in Firefox. This comes from the 3D lighting filter code in Firefox, which you can apply to your text and get cool shadowing effects. And in this case, we don't care about almost all of the code. We care about this line in particular. And we care about this line for a couple of reasons. First is I see multiplies and divides. And I showed you performance tables a second ago that indicate we can see performance variation in multiplies and divides. And this is in fact floating point math. It's single precision floating point math. More frustratingly, this is an attacker-controlled parameter. When the adversary asks the browser to do this filter rendering, they can specify any value to go in this argument. And then this is secret pixel color data that the adversary is not allowed to inspect. So if we want to instruct an attack here, what we do is we put a subnormal floating point value into this attacker-controlled parameter. We construct a scenario in which the secret data is either 1 or 0, and this is possible in most browser contexts. And then we can start looking at our performance tables. Well, this multiply is going to take either 6 cycles or 130, and this divide is going to take either 6 cycles or 152 cycles. And so we can sum all of this up, and we get a 270 cycle timing delta between whether that pixel was black or white. This line of code compiles down to essentially 2 math operations. There's no branching in this. This is why an instruction data timing side channel is a scary thing to deal with, because you can't see it if all you did was look at the source code without knowledge of the processor architecture and behavior. I will note one thing about this, which is the adversary needs to measure an 85 nanosecond timing difference. 270 cycles is not actually very much. That's okay. What the adversary does in this particular case is just repeat the operation a whole bunch of times. So they do it across an 800 by 800 copy of the pixel, raising the timing delta up into the tens of millisecond range, which the adversary can easily detect. So we now have all of these pieces in place, right? The adversary picks one of these filters, isolates a pixel, and then is able to run this, and then they're able to extract content out pixel by pixel. Anything that they can put into an iframe, they can read the data out bit by bit. So we demonstrated vulnerabilities in Safari, Firefox, and Chrome for this. What's a little bit interesting about these particular vulnerabilities that I've listed here are that this is our second round of vulnerabilities. We published kind of our first proof of concept attack against Firefox in 2015. And 2 years later, I came back, and the browsers had deployed defenses against these specific attacks. And then we wrote variations on those attacks that continued to work and found new vulnerabilities in all of these browsers. And I'd love to talk kind of in one-on-ones about reporting the same vulnerability to 3 different vendors with 3 very different responses to that vulnerability. So I promised you that we were going to talk about defensive systems. So let's talk about solving these problems. And an immediate approach here might be, maybe we can just keep making things constant time. Maybe we can write like safe, constant time floating point math. And we don't have to do anything drastic. And this is actually what Chrome tried to do. The problem is that it takes incredibly deep knowledge about how not just your processor, but every processor you're going to run on executes floating point instructions and what can cause timing variations. This is effectively impossible to scale. It also breaks the entire concept of having abstraction layers because now you're embedding into your application detailed knowledge for security purposes of every single chip architecture that you might execute on. So this is not a particularly good idea. As a bit of a side note, we did try and work with integer math as well. You can do a little bit better there, but you can't actually completely solve the problem either. So we can also take a kind of a different approach to trying to solve this problem. And what we're going to do instead is we're going to invalidate the attacker's assumption that they can accurately measure time. And so this will give us the ability to mitigate not just a specific timing channel, but mitigate any timing channel, even if we don't know what the adversary is trying to do. And this observation comes from the fact that the adversary who is running in this environment doesn't actually have very much insight into our system. They're running a web page, which means we, as the defender, the person working on the web browser, have significant control over how the adversary sees the world. And so while there may be all of these sources of timing leakage that are rising up through the system, it is perhaps the case that we can build a different abstraction and notion of time in the application, present that to the adversary, and this timing leakage is no longer useful. And so what we're going to do is alter the adversary's ability to measure time. We're going to assume that the adversary has some incredibly clever way to leak timing information and just make it impossible for them to do that. Now, the good news is that there is actually a principled way to do this that we're going to be adopting, but we need to do this in a principled way. We can't be naive. And I'm going to explain to you kind of like why that is. So we're not the first ones to notice that this is a good approach. This actually comes from 2015. The Tor web browser, which is a privacy and security focused web browser, rounds down the notion of time to 100 millisecond intervals. So when you, as a web page, ask for what time it is from the browser, you get it back as 0, 100, 200, 300, 400 milliseconds. We should ask ourselves, does this actually obscure our notions of time? So if we consider instead a rounded down 1 hour clock, and you were to ask me what time it is repeatedly, and I tell you that it is 4 o'clock, 4 o'clock, 4 o'clock, 5 o'clock. When I say 5 o'clock, you actually have quite a bit of certainty about what time it is. You don't have an hour of uncertainty because you saw the transition from 4 to 5. And so we can formalize this notion into something that we call the clock edge technique. We're not the first to notice you can arbitrage between timing systems here, but we kind of formalize it and apply it to a whole bunch of different things. So we have in this situation a major clock that has a known timing granularity and period. So our 100 millisecond Tor browser clock or our 1 hour you ask me clock. And then we have a minor clock that runs at some unknown frequency and is probably hard on the system to run. So if you're asking me what time it is, you're not doing anything else. And we're going to first have a learning phase where the adversary is going to wait until they see a major clock transition, thus the clock edge technique. They're going to then start the minor clock and run it until they see another major clock transition. They then count up how many times they saw the minor clock tick in there. So in this case, they saw 8 transitions. And then when they want to measure the duration of event, what they will do is, again, align on a clock transition because that's when we know exactly what time it is. They will start the target event that they want to measure the duration of. And when it completes, instead of saying it took between 1 and 2 major clock ticks, they will immediately start the minor clock and run it until the next major clock change. Do a little bit of subtraction and division, and you see that the target ran in about 1 1/4 major clock ticks, or 125 milliseconds in the 100 millisecond browser example. Now, you can implement this in about 15 lines to 20 lines of JavaScript. What you do is you have a while loop with an incrementing variable, and the incrementing variable is your minor clock, and your major clock is just asking the browser what time it is. And so we can run this against a web browser and see how it does in reality. And so on the x-axis here, we have the actual duration of some event. And on the y-axis, we have what some time measuring technique told us the event took. So if the technique is perfect, it'll just be an x equals y line because it'll always tell you exactly how long the event took. If we run this again with just that rounded down 100 millisecond clock, we get a step function that's below the x equals y line at 100 millisecond intervals. This is exactly what we would expect to see. Now, when we use that little bit of JavaScript to do the clock edge technique, we get vast improvements in timing accuracy for the adversary. They're able to go from 100 milliseconds of uncertainty to 100 microseconds or less of accuracy. And in fact, other people have used our technique here to resurrect previously impossible timing side channels. So, as I promised you, there is a principled method for doing this. We can use a proven technique. And what we're going to do is we're going to adopt some techniques from the VAX security kernel project in the early 90s, late 80s. They had a similar problem, and they have an interesting approach to a solution, which is called fuzzy time. Now, the idea of fuzzy time is we're going to first start with one of these rounded down clocks. Let's assume it's our 100 millisecond granularity rounded down clock. We do not make this clock visible to the adversary. Instead, we are going to construct an alternative clock that is going to be updated at semi-randomized intervals based on the real clock's value. And then we make this observed clock visible to the adversary instead. Now, there's a couple of nice things about this. The first is if we've been choosing our clock updates in a principled way, our clock is actually still useful. We haven't just removed it from the system. It's only ever behind, it's never ahead, and it's only ever behind by a bounded amount. The other thing is that something like the clock edge technique will no longer function because those transition points where we knew exactly what time it was have been blinded and shifted unreliably forward somewhere. Now, we can't just do this to just the clock in the system. We actually need to do it essentially to everything in the system. So that's I/O, events, network, all of these sorts of things. Everything kind of has to operate in this staggered manner. Now, if we do that and we do it correctly, we get kind of a cool guarantee, which is we get a provable upper bound to the number of bits per second that an adversary can learn, regardless of what clever timing side or covert channel they have. And this comes kind of from the original fuzzy time work here. So with fuzzy time in mind, we can talk about how this concept can apply to a web browser and why it's useful. So this is meaningful for us because we're talking about a context, as I kind of alluded to earlier, where the adversary is not on a binary scale of success. They don't just win or lose, compromise your system or not. They're attempting to steal information about users, and they're trying to build fingerprints. The more bits of information the adversary gets, the better they do. And so we can bound how many bits they can get by doing this. There is an additional benefit, which is that some attacks that require really fine-grained timing simply stop functioning, but that's not a provable guarantee in the same way. So I built a prototype web browser called Fuzzyfox, which is unsurprisingly a set of modifications to the Mozilla Firefox web browser to implement the fuzzy time concept in a very different situation. And so what we need to do here at a high level is two broad categories of changes. The first is make the browser's explicit notion of time fuzzy. And the second is to make all events in the system occur at kind of fuzzy intervals. And this required us to make kind of a lot of core changes to the way that Firefox functioned. So at a theoretical level, at least, the explicit time changing here is relatively straightforward. We are going to construct one of these observed clocks. We will then alter the core of the browser's notion of time to follow this observed clock. And we then propagate that notion of time out to the rest of the browser architecture. Now, we do need to make sure that we are careful and we only have one canonical source of time. If we have more than one canonical source of time, the adversary is going to arbitrage between them. And you have two fuzzy clocks, and that's not good. Far more invasive is that we have to modify the way that Firefox thinks about executing events. So the core of the browser is this event queuing system. This is everything from page loads to connections to JavaScript execution, animations. We're going to create a series of implicit time epochs and then map these epochs into these fuzzy time regions and update them, end each epoch at a clock transition. And we need to make it so that during an epoch, the concept of time does not advance forward for any event that is executing. It only advances at these boundaries. So this is not super straightforward, and it's not without some side effects in terms of the performance of the web browser to make these changes, but it is possible to make them, and you do end up with a usable browser out the other end. And you can tune the performance versus security trade-off. So the advantage of building a prototype is that we can take our previous attack attempts and timing techniques and try them against it. So this is what happened when we ran it against the old 100 millisecond rounded down browser. We used our clock edge technique to improve the accuracy. And if you do the same thing on Fuzzyfox, you no longer get useful improvements. One thing that was kind of neat is actually the result we get out here is completely consistent with what the theory tells us should the adversary's accuracy be. So that was a good kind of indication of the engineering effort that went into this. So kind of after we built this, there's been a non-trivial amount of adoption of these ideas, which has been quite good to see. So Chrome and Edge independently adopted fuzzy clocks in their system. And they did this as a response to the kind of high-profile Spectre and Meltdown vulnerabilities in 2018. They needed a way to damage the adversary's ability to tell time in a consistent and meaningful way, and they turned to a fuzzy time technique, although they both implemented their own variations of this. More excitingly is that Firefox has not only adopted the explicit time fuzzing techniques, I worked with them a bunch kind of after publication on this, but they also re-implemented the entire Fuzzyfox prototype as a like beta nightly feature in Firefox, and they did that internally at Mozilla in collaboration with us, which was really cool. And they're kind of continuing to use our way of thinking about this problem and solution space to talk about timing attacks and damaging adversaries' abilities. So what's neat fundamentally about fuzzy time is that we haven't had to completely break our abstraction layers, right? We were able to do this without in-depth knowledge of the hypervisor or the chip architecture, and we're able to build an alternative abstraction of time just in the application and present that to the adversary and get a meaningful guarantee out of it. So for the last project I'm going to talk about here, we're going to change gears a little bit because we have a slightly different scenario we're going to be considering. So we're going to assume, as usual, that the system we are building on has leaky abstractions, and we're going to try and build a trusted system from the ground up anyway. And we're going to do this by choosing carefully what and how we're trying to defend parts of our system. So rather than try and defend the entire stack of things, we're going to choose the parts of our application that are relevant to our security properties. So maybe just our cryptographic library is critical to the security objectives of this application. And we're going to be concerned here not just with timing side channels, but kind of all normal software attacks and numerous other types of side channel and unusual attack techniques. And so the question becomes, okay, what is the efficient way to defend these applications and specifically these isolated application components? And the answer here is to think carefully about what we're trying to do. If what we do is say, well, we're trying to defend the cryptographic library, but the rest of the application, we're not as worried about these attacks. So we'll draw our trust and defense boundary like this. We have not significantly improved the situation. We've removed part of the application from things that we need to trust and need to defend, but we still need to defend all of the rest of the system, which is not, as I said, improving the situation too much. So the alternative approach is that we're going to take the privileged software stack. We're going to move it to the side. We're going to keep it running on the system, but we're not going to trust it. We're instead going to trust only our isolated component. We will call this an enclave. And we will root that trust in the hardware itself. And this approach is called trusted execution environments, or TEEs. And the idea here is that they are a security mechanism and primitive that provides partitioned and isolated execution. It grants additional security protections. And all of this is done with an explicit kind of performance and functionality versus security trade-off. And as somebody working in security, this is very appealing because it means we're in a world where people want to take a specific set of functionality and performance trade-offs for additional security. And so we can apply kind of strong protections. Now, unsurprisingly, since these are rooted in hardware, there are a number of TEs out there from hardware manufacturers. So ARM has a system here called TrustZone. This is on all of your Android smartphones, if you have one. Intel has a system called SGX that is starting to get more well-known at this place. This is actually where the nomenclature of enclave was popularized, is from SGX's design. And AMD has something called SEV that is designed around primarily virtualization techniques. Now, all of these are actually quite different from each other in what they're trying to protect, like the size and type of thing, and how and what they are protecting it against, what adversaries and attacks they're defending against. But they all have similar high-level objectives of kind of moving the privileged software stack out of the trust boundary and applying these additional protections to these isolated components. Now, this unfortunately is not perfect in the current world. And we have some challenges with the way these systems are currently designed. And they're well illustrated by SGX as an example. So in Intel's SGX, they defend against an adversary who is extraordinarily powerful. They've dedicated hardware defenses to keep an adversary who can reach into your computer, physically touch and modify all memory on the system. They defend against that, so your application is safe. You take a huge functionality hit for your application for this defense. It's not cheap. At the same time, SGX makes absolutely no attempt to defend against any sort of even basic side channel. And in fact, the construction and design of SGX makes side channels easier to launch than against normal applications. So they chose this set of trade-offs because it made sense for their design and their specific use case. The problem is that this is a fixed set of trade-offs. If you want to run on an Intel processor, you have to take that set of functionality and performance hits for their specific security guarantees. And so you are tied to that set of trade-offs the moment you choose a chip manufacturer. And this is problematic when we think about how widely the security world wants to use trusted execution environments. They're rapidly becoming a cornerstone of secure system design, and they're in everything from kind of little edge devices that are just a little sensor, and they're only concerned with a network adversary who is attacking them over the Wi-Fi, all the way up to cases where people want to run machine learning models inside of these enclaves on cloud data servers, and they're worried about other cloud tenants trying to steal their data, or even malicious cloud providers. Now, these two ends and everything in between need different functionality and performance trade-offs, and they are concerned with protecting against different types of things. And so we want to be able to give these situations a T primitive without kind of building it again every time. This gets us to this notion of kind of building a flexible TE. And the project I've been working on in this space is called Keystone. And so how do we build a more flexible trusted execution environment? There's a kind of a handful of requirements at a high level we can think about. The first is that hardware must not be managing our security policies. It must be the case that hardware is simply providing a set of strong security primitives. We need stronger security than kind of the normal execution model, but we don't want hardware to make a preset set of decisions about how that primitive should be applied. And then those policies and functionality should be per application and per enclave. So if we have only one set of trade-offs on a hardware platform, we're still stuck at the SGX model where we can't customize it to the application and use case needs. Now, the good news about this set is this means we really only need kind of one thing from the hardware, which is these strong security primitives, and everything else we can do in software. And so the insight we have here is that we should be separating the security mechanisms from the policy decisions and enforcement of those mechanisms. So that means we want kind of unopinionated hardware primitives. That is, hardware mechanisms for security that don't have a strong notion of how you're going to use them. They provide a simple isolation mechanism, a simple protection mechanism that then a minimal software layer will manage and compose to create stronger security guarantees. Now, the project that we've been building out of this Keystone has relatively lofty goals. The objective is to be the platform for trusted execution environment research. We think that this style of design will drastically accelerate the ability to do research in this space. We also want to be the standard for what's called RISC-V secure systems. And that's because Keystone is a framework for building trusted execution environments on RISC-V based hardware. Now, RISC-V is an up and coming hardware design out of Berkeley primarily. It's been seeing wide adoption in things like hard drives and phones already, and it's kind of continuing to grow fast, which gives us a really good opportunity to get in on the ground and build secure systems for this from the beginning. Now, in Keystone, we're taking advantage of kind of two core things in RISC-V, which is why we're building it there. The first is what's called machine mode, which is a high privilege execution mode that runs below the kernel and below the hypervisor, but above the hardware. But it's easy to write software for this mode. You can just write C code or Rust code, and it executes in this mode. It executes exclusively on physical memory. And the second is a mechanism that RISC-V provides called physical memory protection, which allows us from machine mode to easily apply flexible permissioning to physical memory regions, completely ignoring the virtual memory translation system. And so what Keystone builds on top of this is kind of two layers of modular privileged software. The first is what we call the security monitor. And this runs in the machine mode and provides the interface to the hardware and composes our security primitives into security mechanisms. And the second is a set of enclave-specific kind of kernel mode runtimes. And these allow each application and enclave to tune its functionality and security and performance needs kind of per use case. So the benefits as we see it is that this gives us the ability to build a set of kind of customized TEs for every individual deployment. Even given a particular hardware platform, we can actually instantiate a whole bunch of different trade-offs bases just from one set of hardware. This means it also lets us do really rapid prototyping. So if we have hardware that we want to try and evaluate or software changes that we're interested in doing to TEs, a couple hundred lines of code, and you can integrate those changes into Keystone. It also makes us more reactive to threats because we can patch in software rather than ship new hardware, since essentially all of Keystone is in software. So this is not just a kind of a proposal. We've built a whole bunch of system stuff to make this work. There's been a huge systems building effort over at Berkeley by our group. The first is kind of this layer of stuff to make applications possible in Keystone. So this is SDKs, tooling, documentation, demos, Docker images, examples, all of that kind of stuff needed to get an application running inside of here. The second is this modular microkernel layer. This is what allows each enclave to make its own set of functionality trade-offs, as well as apply additional security mechanisms in kind of a transparent way. And then lastly is kind of the heart of Keystone, which is the security monitor. It's a reference monitor style design. Its job is to interface between the hardware security primitives available and the enclave and compose strong security mechanisms. So this is what creates the concept of an enclave in Keystone. One of the advantages of this is, like, for example, on the development hardware we've been working on, this allows us to support protection against cache side channels by composing kind of some customizable hardware that's in there and common in embedded systems with the physical memory protection system to create a private cache partition. And speaking of our dev board, you can run Keystone on lots of different stuff. There's our current hardware dev board. There's some new hardware that Microchip is putting out in like May that we'll be able to run Keystone on soon. There's FPGAs. You can run it on local FPGAs. You can run it in the cloud. You can run it in emulation. It takes a couple hours at most to get a full development environment set up using all of our tools. Now, part of this and part of trying to be a platform for research is based on community. So this is a picture from the second of 2 annual workshops I co-organized around kind of open source secure hardware and systems. We've had huge buy-in from industry. We had talks from Intel, AMD, or Intel, ARM, Microsoft, I think, Google, a whole bunch of different folks. And then a ton of academics as well came and participated in both of these. And this has borne itself out. We've got people forking our system, working on it, contributing back. We've gotten contributions from a university in Japan who wanted to run Keystone on some local FPGA instances. We didn't have support for that. They contributed back the instructions and details necessary to do that. And so Keystone is what provides us kind of this way to build flexible, security-aware abstractions at several different layers of the system to compose a trusted system from the ground up, or a variety of different use cases. So this gets me kind of to future directions. And I'm going to mention a couple different things that I've been thinking about on different timescales. The first is that I told you that Keystone has this kind of modular microkernel layer. It makes it pretty easy to apply defenses to an application without modifying the application. And so I'm interested in taking this fuzzy time concept that I've done a bunch of work with before and applying it here. So the idea would be that an application would be protected from accidentally leaking information through timing based on its communication with the rest of the system. And there's some interesting engineering questions and kind of research questions about how we can build this in here and what specific guarantees we will get out of such a system and how we can tune the performance versus security trade-off. Staying on the theme of Keystone, I'm also very interested in working very closely with people in hardware architecture on alternative hardware security mechanisms and execution modes. So Keystone makes it really easy for us to say, when we're running this enclave would like an alternative hardware execution mode. It would like different hardware defenses. And so that allows us to apply those mechanisms where they're needed with the lowest possible performance impact. And so especially kind of in the post-Spectre meltdown stuff, I'm very interested in working closer with hardware architecture on that. Now, those are both on the defensive side. On the more adversarial side, I've actually worked for several years on some stuff around the security model of FPGAs in cloud data centers. So FPGAs are customizable hardware. They're now rentable from Amazon or Microsoft, just like a regular cloud machine in many ways. However, unlike CPUs and classical servers, we don't really have a good sense of what attacks are possible in this context. Early results in research are really starting to show that there are a new class of problems and attacks that happen when you deploy an FPGA in a data center. And so we need to start drilling through this from the security side to understand what problems there are, how easy it is for an adversary to do different sorts of things. And then with that knowledge, we can go back and propose a secure and safe way for FPGAs to be deployed in a cloud environment for both users of the FPGAs and of the cloud hardware. This is a bidirectional problem. So these pieces fit into the same kind of pattern I've been talking about here, which is we need to drill through, identify problems, and then talk about how we can build safer systems on the other side. And then we need to then take those insights, right, and get them out into the wild in front of users. So I got the chance to talk about kind of 3 of these projects today. They required everything from kind of web security to architecture. And so this is not possible without a fantastic group of collaborators. Everything from programming languages, architecture, systems, cryptography, FPGAs, obviously security. So a huge thank you to all of my collaborators, and a thank you to you all for joining me on the call. And with that, I will be going to questions. Thank you.
Great. Let's everyone unmute your microphone so that we can actually thank David, because this is one of the things that we can't do in and then you can go ahead and mute your microphone again. And let's use the chat feature, as I mentioned. Just type hand to raise your hand. I'll give a moment pause to. Okay, Joseph.
My mic on?
Oh, yes.
Okay, great. So in the notion of fuzzy time that you present, it has this really great thing of this provable upper bound of the bit leakage over time.
Yes.
So we can bound how much secrets leak. This is great because it empowers systems designers to choose what an acceptable bound is. The problem is, how do you choose that bound? When it's wired into the web browser, now it's one size fits all. If something's being rekeyed every 15 minutes, that's a great bound. If I have some key that's distributed everywhere and it takes 40 days to crack, but once you crack it, like my whole cloud system is donezo, that 40 days is fine to crack it. So how do you choose a bound that works for everyone?
So there's a couple things I want to answer in that question. The first is that the scenarios we envision fuzzy time being successful at defending users against are situations where we're talking about privacy leakage and not key extraction. So key extraction is a scenario where we're talking about the adversary needing to leak tens of bits, and fuzzy time is not super effective at that unless you crank it up to a level that makes the browser relatively unusable. What it is effective at doing is stopping the adversary from leaking your browsing history, from stealing documents, from that type of leakage where the adversary needs to leak a large number of bits. Now, as to tuning it correctly, you're totally right. There's a couple different approaches to this. I'm an advocate in web browsers in general of kind of having two modes of execution. One that is a high performance kind of, you're running a HTML5 Flash game and you clicked the, yes, I trust this web page to do something, to like get access to all the high performance stuff, and a regular browsing mode where many of the APIs and services a browser provides would be severely degraded in performance. They would still be allowed to execute. And in those scenarios, we have a situation where we can say, okay, in the normal browsing mode, we do not incur too much of a performance hit and usability hit in the browser. We tune down this clock so that the granularity is small, the number of bits per second is higher, and in the other scenario, we allow the adversary to, I'm sorry, yeah, in the inverse there. But the idea being that if you have multiple execution modes, you can also choose a default that won't impact users in general, but provides a reasonable level of guaranteed protection. The other approach here, right, is something like Chrome and Edge, which is just apply it to your clocks, in which case your performance hit is incredibly low because you're not applying it to the event subsystem and JavaScript execution, but you still are damaging the adversary's ability to tell time. You're just not doing it kind of in a global way.
Great. Well, thank you. I don't see more hands, and I also know that it's now just at 4:30. So if everyone wouldn't mind unmuting again, and we can thank David one more time.
Thank you.
Thank you, David, for joining us virtually. I know this was a very unusual setup, and I thank you all the audience members for joining us as well. Yeah, thank you, everyone. And David, I'll connect with you afterwards.
Awesome. Thank you.
Thank you, everyone.
Still loving that cone head, Yoshi.
Sorry? Thank you. Okay.